Welcome to this quiet journey through the cosmos. A gentle exploration designed for those peaceful moments when the day has ended and the night stretches out before you like an endless ocean of possibility. Wherever you are right now, whether you are lying in bed with the covers pulled up softly around you, or sitting in a comfortable chair with the lights dimmed low, or perhaps resting on a couch, in that perfect position where your body feels weightless and supported all at once. I invite you to settle in completely. Let your shoulders drop away from your ears. Let your jaw unclench if it has been holding tension. Let your breathing slow down to match the rhythm of calm waves touching a distant shore. Feel the surface beneath you supporting your weight entirely, so that you do not have to hold yourself up anymore, so that you can simply exist without effort in this moment. Tonight we are going to drift together through the vast quietness of space, not rushing or chasing after facts and figures, but floating peacefully through some of the most extraordinary and rare phenomena that exist anywhere in the universe. We will visit places that are so uncommon, so special, so incredibly unlikely, that their very existence reminds us of how strange and wonderful reality can be. But we will take our time getting there, moving slowly like a spacecraft drifting on momentum alone through the silent vacuum between the stars, letting each concept settle into your mind gently before moving on to the next. There is no hurry in the cosmos. The universe has been here for nearly 14 billion years, and it will be here for trillions more. And in that vast expanse of time, this moment right now is yours to simply be at peace, to let your thoughts become as soft and diffuse as a nebula, to allow yourself to sink deeper into comfort with every breath you take. So close your eyes if you have not already, or let them rest half open and unfocused on some dim point in the room. And together we will begin our slow journey outward from Earth, leaving behind the bright lights and loud sounds of daily life, ascending gently through the atmosphere, rising past the edge of space where the sky turns black and stars appear in countless numbers, and then continuing outward into the cosmic ocean where distance is measured in light years and where silence is the only sound that exists. We begin now, drifting peacefully toward the rarest things that the universe has ever created. What makes something rare in an infinite universe? When we look up at the night sky from our small planet, we see thousands of stars with our eyes alone, and billions more through telescopes, spread across a universe so large that light itself takes billions of years to cross from one side to the other. In such an immense cosmos, filled with more stars than grains of sand on all the beaches of Earth, you might wonder how anything could possibly be considered rare. After all, even if something happens only once in a billion times, with billions of galaxies each containing billions of stars, that rare event should still occur in countless places scattered throughout space. And yet, even in this vast universe, there are phenomena so uncommon, so particular in their requirements, so delicate in their balance of conditions, that they occur only in the tiniest fraction of places, or perhaps only once, or perhaps not at all anymore, existing only as memories encoded in light still traveling through the void. Rarity in the universe is not about absolute uniqueness in the way we might think of it on Earth, where a single painting exists or a single human being lives. Instead, cosmic rarity is about probability stretched across unimaginable scales, about combinations of circumstances so specific that even in a universe with more stars than we can count, they remain extraordinary. Some things are rare because they require such precise conditions that only one place in a trillion meets those requirements. Other things are rare because they exist for only brief moments in cosmic time, flashing into being and then disappearing so quickly that catching them is like trying to see a single raindrop in a storm that lasts for eons. Still others are rare because the universe itself has only recently become old enough for them to form, or because they represent such extreme versions of normal processes that they push against the very limits of what physics allows. As we drift through this documentary together, moving slowly from topic to topic, like a spacecraft making lazy orbits around distant worlds, we will encounter all of these kinds of rarity. We will visit galaxies that exist in such profound isolation that no other galaxy has influenced them for billions of years. We will examine stars that burn with such unusual chemistry that they seem to belong to a different universe entirely. We will explore planets whose properties seem impossible, whose very existence challenges what we thought we knew about how worlds can form. And through it all, we will maintain this gentle pace, this quiet contemplation, allowing each wonder to settle into your awareness without rushing, without pressure, without any need to memorize or retain, simply experiencing the strange beauty of the cosmos as one experiences a sunset or the sound of rain, present with it for this moment, and then letting it pass peacefully as we move on to the next quiet marvel, the void between galaxy clusters. Let us begin our exploration of cosmic rarity by drifting into one of the emptiest places that exists anywhere in the universe. A region so vast and so devoid of matter that if you were to somehow find yourself there, you would float in darkness so complete that not a single galaxy would be visible to your eyes in any direction. These regions are called cosmic voids, enormous bubbles of nearly empty space that exist between the great clusters and superclusters of galaxies that make up the large-scale structure of the universe. To understand how rare and strange these voids truly are, imagine first the universe as it appears on the largest scales, not as a random scattering of stars and galaxies, but as a vast cosmic web, a three-dimensional network of filaments and walls where galaxies gather in long chains and sheets, clustered together by gravity over billions of years. These filaments stretch across hundreds of millions of light years, connecting massive galaxy clusters like glowing threads in a dark tapestry. And where these filaments intersect, enormous superclusters form, containing thousands of galaxies bound together by their mutual gravitational pull. But between these filaments, between these walls of galaxies, there exist the voids, regions that contain almost nothing at all. The largest of these voids span 300 million light years or more from one side to the other. Volumes of space so immense that you could fit thousands of galaxies the size of our Milky Way inside them, and still have them be effectively empty. Within these voids, matter is so scarce that the average density is only about 10% of the already low density of the universe as a whole. There might be one or two small galaxies scattered through such a void, isolated islands of light separated by distances so great that light from one would take tens of millions of years to reach another, but mostly there is simply nothing. Just the faint wisps of intergalactic gas so thin that it contains only 1 atom per cubic meter, and sometimes not even that. These voids are among the quietest places in all of existence. Regions where nothing happens, where no stars are being born, where no galaxies are colliding or merging, where the universe exists in a state of profound stillness that has persisted unchanged for billions of years. If you could somehow drift through such a void, traveling for millions of years at the speed of light, you would see nothing but blackness in every direction. No stars to mark your progress, no galaxies to give you any sense of place or movement, only the unchanging emptiness of space itself. The isolation of these regions is total and absolute, and yet they are not rare in the sense of being few in number, for voids make up most of the volume of the universe. What makes them rare and special is their effect on the galaxies that do exist within them. The handful of lonely galaxies that have formed inside these vast, empty regions and that have evolved in complete isolation from the rest of the cosmic community. Lonely galaxies in the cosmic voids, drifting through the endless darkness of a cosmic void. Let us imagine now that we come across one of the rarest types of galaxies in the universe. A void galaxy. A small island of stars existing in profound isolation, billions of light years from any other significant collection of matter. These galaxies are rare, not because few of them exist, for there are hundreds of thousands of void galaxies scattered through the empty spaces between the cosmic web's filaments. But because they represent a unique evolutionary path that most galaxies never experience. Most galaxies in the universe live in what we might call crowded neighborhoods, surrounded by thousands of other galaxies within a relatively small volume of space, constantly interacting through gravity, occasionally colliding and merging, being shaped by their environment in countless ways. But void galaxies have never experienced this. They formed in regions where matter was already sparse, where the collapse of gas into the first stars happened slowly and inefficiently, where no other galaxies existed nearby to influence their development. As a result, they have evolved in almost perfect isolation for billions of years, never colliding with another galaxy, never having their gas stripped away by a hot intergalactic medium, never being tidally distorted by close encounters with neighbors. They are, in a very real sense, pristine examples of what a galaxy looks like when left entirely alone to evolve at its own pace according to its own internal processes. These void galaxies tend to be small, often containing only a few billion stars compared to the hundreds of billions in a large galaxy like our Milky Way. They are usually spiral or irregular in shape, rich in gas because that gas has never been removed by external processes. And they often show signs of active star formation, their gas slowly collapsing into new stars at a steady, unhurried rate that could continue for many billions of years into the future. Their isolation gives them a quality of peace, as if they are the introverts of the cosmic community, content to exist quietly in their own space without the drama and chaos that characterizes the lives of galaxies in denser regions. Studying these void galaxies teaches us something important about rarity itself, about how the absence of something can be just as significant as its presence. These galaxies are rare, not because they possess some exotic property or extreme characteristic, but because they represent a path not taken by most of the universe. A quieter story playing out far from the main action. A reminder that even in a cosmos filled with violence and transformation, There are places where change comes slowly and gently, where billions of years pass in relative stillness, where the universe simply exists without drama, patiently turning its gas into stars one at a time, over eons of peaceful solitude. Stars made almost entirely of hydrogen and helium. As we continue drifting outward through the cosmos, moving slowly from one wonder to the next, let us turn our attention now to a different kind of rarity, one that exists not in the emptiness of voids, but in the nature of stars themselves, specifically the rarest stars in the universe. Those that are made almost entirely of just two elements, hydrogen and helium, with almost no heavier elements at all. These stars are so rare that astronomers have found only a handful of them despite searching through millions of stars. And they are considered precious treasures of astronomical research because they offer us a glimpse into the very earliest epochs of the universe, into a time when the cosmos was chemically much simpler than it is today. To understand why these stars are so special and so rare, we need to drift back in time, back through billions of years of cosmic history to the period shortly after the Big Bang, when the universe was only a few 100 million years old. At that time, no stars had existed long enough to die and scatter new elements through space. And so the gas clouds that collapsed to form the first generation of stars contained only the elements that had been created in the Big Bang itself. Primarily hydrogen with some helium and tiny traces of lithium, and nothing else. No carbon, no oxygen, no iron, no silicon, none of the heavier elements that make up planets and people and all the complex chemistry of life. For those elements had not yet been forged in the nuclear furnaces of stars. The first stars that formed from this primordial gas were enormous, hundreds of times more massive than our sun, burning incredibly hot and bright and dying quickly in catastrophic supernova explosions that scattered the first heavy elements into space. Those heavy elements then mixed with the remaining primordial gas, enriching it, changing its chemistry, and from that slightly enriched gas, the second generation of stars formed, which also eventually died and added more heavy elements. And so on through many generations until we reach the present day, when the gas clouds that form new stars like our sun contain about 2% heavy elements by mass, a small amount, but enough to profoundly affect how stars and planets form. The stars we see around us today are all part of these later generations, formed from gas that has been enriched by countless previous stellar generations. And so they all contain significant amounts of heavy elements in their outer layers, visible in their spectra as the distinctive patterns of absorption lines created when light passes through their atmospheres. But somewhere out there in the galaxy, there should still exist a few stars from the very earliest generations. Stars that formed from gas that was only barely enriched with heavy elements, containing perhaps 100,000th or even 1,000,000th the amount of carbon and oxygen and iron that our sun has. These would be the oldest stars in the universe, relics from an earlier age, and finding them is one of the great quests of modern astronomy. The difficulty is that these ancient stars, if they exist and have survived to the present day, would be very small and faint. For only small stars can live long enough to still be shining after 13 billion years. And small faint stars are hard to find among the billions of brighter stars that crowd our telescope's fields of view. The search for ancient survivors, drifting now through the disk of our own Milky Way galaxy, We can imagine the work of astronomers who spend years searching through massive catalogs of stars, looking for the telltale signs of these ancient survivors. These stars with almost no heavy elements that would mark them as members of the universe's earliest stellar generations. The search is painstaking and slow, requiring careful analysis of the light from thousands of stars, measuring the tiny absorption lines in their spectra, calculating the abundances of different elements with great precision. Most stars show the expected amounts of heavy elements, the roughly 2% by mass that indicates they formed relatively recently in cosmic history, within the last few billion years. But occasionally, very occasionally, a star is found with only a tiny fraction of that amount, perhaps 1/100th or 1,000th the sun's heavy element content. And these stars become objects of intense study, their properties measured and analyzed, their motions through the galaxy tracked to understand where they came from. The rarest of these stars, the ones with the lowest heavy element content ever measured, can be counted on two hands. They are scattered through the halo of our galaxy, moving in elongated orbits that carry them far above and below the galactic disk. Ancient wanderers that have been circling the Milky Way since before the disk itself fully formed. When astronomers study these stars closely, they find that they are indeed very old. Their age is estimated at 12 or 13 billion years, making them nearly as old as the universe itself. They are small stars, red dwarfs mostly, with only a fraction of the sun's mass, burning their hydrogen fuel so slowly that they could continue shining for trillions of years into the future, long after larger stars like our sun have exhausted their fuel and faded to darkness. In their atmospheres, the amounts of carbon and oxygen and other heavy elements are so low as to be almost undetectable, sometimes less than 1/10,000th of what we see in the sun. Clear evidence that these stars formed from gas that had been enriched by only a few previous generations of stars. Gas that was still very close to its primordial composition. Studying these stars allows astronomers to probe the conditions in the very early universe, to understand how the first stars enriched the cosmos with heavy elements, to trace the chemical evolution of galaxies over cosmic time. Each of these ancient stars is like a time capsule, preserving in its outer layers a sample of the gas from which it formed billions of years ago. A fossil record written in starlight that we can decode through careful spectroscopy. The rarity of these stars makes them precious beyond measure, for there are so few of them, and they offer us our only direct connection to the universe as it existed in its youth, when galaxies were just beginning to form and the cosmic web was still taking shape and the chemistry of space was vastly simpler than it is today. Planets around ancient stars, continuing our slow drift through cosmic rarities. Let us consider now an even more unusual possibility: the existence of planets orbiting these ancient metal-poor stars, worlds that would have formed from the same primordial gas as their parent stars, gas almost entirely devoid of heavy elements. The question of whether such planets can exist is one that pushes at the boundaries of our understanding of planet formation. For the standard model of how rocky planets form depends critically on the presence of heavy elements, specifically elements like silicon and iron and magnesium that can condense into solid grains in the cooling gas around a young star. Grains that then stick together and grow into larger and larger bodies, eventually forming asteroids and planetesimals, and, given enough time and material, full-sized rocky planets like Earth. But in gas that contains almost no heavy elements, this process would be extremely difficult, for there would be almost no solid material available to form those initial grains. The gas would be nearly pure hydrogen and helium, which cannot condense into solids at the temperatures found in protoplanetary disks. And so any planets that formed would likely be entirely gaseous, similar to Jupiter, but perhaps even more purely composed of hydrogen and helium, with no rocky core at all, no ices, no heavy element enrichment whatsoever. Such planets, if they exist, would be among the rarest worlds in the universe. Gas giants of nearly primordial composition, time capsules from the universe's youth, preserving in their atmospheres samples of gas that has remained almost unchanged since shortly after the Big Bang. Astronomers have searched for planets around metal-poor stars, using the same techniques of transit observations and radial velocity measurements that have been so successful in finding planets around more typical sun-like stars. But so far the results have been ambiguous. A few planet candidates have been found, but they are rare, much less common than planets around metal-rich stars, suggesting that planet formation is indeed more difficult when heavy elements are scarce. This makes sense from a theoretical standpoint, for with less solid material available, the process of building planets must proceed more slowly and less efficiently, and many protoplanetary disks around metal-poor stars might simply disperse before planets have a chance to finish forming. The few planets that do form in such environments would be special, unusual worlds that challenge our models and force us to think more carefully about the variety of planetary systems that can exist. Imagine drifting towards such a planet now, in your mind's eye, approaching a gas giant orbiting an ancient red dwarf star in the halo of the galaxy, far above the bright disk where most stars cluster. The planet would look perhaps similar to Jupiter, with bands of clouds and swirling storms, but its composition would be remarkably pure, almost devoid of the heavy elements that give Jupiter its colorful clouds of ammonia and methane. The atmosphere would be hydrogen and helium in nearly solar proportions, clear and transparent, except where temperature and pressure create faint hazes, a world stripped down to its most fundamental components, elemental in the truest sense. No moons would orbit this world, for moons are typically made of rock and ice, materials that would be almost non-existent in this system. The view from space near this planet would be strange and isolating, for the star would be small and dim, giving off a reddish light, and the galaxy itself would appear distant and faint, the bright disk seen from above as a flat spiral of light far below, while all around stretches the darkness of intergalactic space, dotted here and there with the faint smudges of distant galaxies millions of light years away. Magnetars, the universe's strongest magnets, shifting our attention now from the oldest and most ancient objects in the universe, let us drift towards something that represents the opposite end of the stellar life cycle. Objects that are very young in cosmic terms, born from the violent deaths of massive stars within the last few thousand years. Objects whose extreme properties place them among the rarest and most bizarre entities known to astronomy. These are magnetars, neutron stars with magnetic fields so incredibly powerful that they defy easy comprehension. Fields billions of times stronger than any magnetic field we can create on Earth, strong enough to distort the very atoms in their vicinity. warping electron orbitals and making chemistry as we know it impossible within thousands of kilometers of their surfaces. Neutron stars themselves are already among the strangest objects in the universe. The collapsed cores of massive stars that have undergone supernova explosions, crushed by gravity to densities so extreme that a single teaspoon of neutron star material would weigh as much as a mountain. A typical neutron star is only about 20 kilometers across, roughly the size of a city, yet contains more mass than our entire sun. Compressed to such incredible density that its protons and electrons have been forced together to form neutrons, creating matter in a state that cannot exist anywhere else, except perhaps in the cores of neutron stars or briefly during the collisions of atomic nuclei and particle accelerators. All neutron stars have strong magnetic fields, for when the core of a massive star collapses, any magnetic field that was present gets compressed along with everything else, and conservation of magnetic flux means that the field strength increases dramatically in proportion to the square of the decrease in size. A star that was hundreds of thousands of kilometers across, compressing to only 20 kilometers, will see its magnetic field amplified by a factor of billions, creating fields thousands of times stronger than even the most powerful magnets on Earth. But magnetars take this to an extreme that makes normal neutron stars look magnetically weak by comparison. A magnetar's magnetic field is typically about 1,000 times stronger than that of a normal neutron star, reaching strengths of 10 to the 15th Gauss, a number so large that it is difficult to grasp, but we can understand its effects by considering what such a field would do. At a distance of about 1,000 kilometers from a magnetar, the magnetic field is strong enough to disrupt the electron orbitals in atoms, making ordinary matter behave in fundamentally different ways. Closer in, within a few hundred kilometers, the field is strong enough to make the vacuum itself behave strangely, becoming birefringent, splitting light into two different polarization states that travel at slightly different speeds. An effect that has been predicted by quantum electrodynamics, but that only exists in nature near magnetars. And on the surface of a magnetar, the magnetic field is so intense that it dominates every other force except gravity, shaping the structure of the neutron star's thin solid crust, creating immense stresses that can cause the crust to crack and shift. And when that happens, the results are explosive. The outbursts of magnetars. Let us now drift closer to a magnetar and observe what happens when the stresses built up in its crust by its immense magnetic field become too great to bear, causing a starquake, a sudden cracking and shifting of the crust, similar to an earthquake on Earth, but vastly more violent. During a starquake on a magnetar, a small section of the crust, perhaps only a few centimeters thick, but extending across several kilometers of the star's surface, suddenly fractures and shifts by a tiny amount, maybe just a few millimeters. This seems like a small event, but the energies involved are staggering. For the crust of a neutron star is incredibly strong, held together by nuclear forces and by the pressure of the incredible density. And breaking even a small piece of it releases as much energy as a large earthquake on Earth, and often much more. When the crust shifts, it disturbs the magnetic field threading through it and extending out into space, causing the field lines to snap and reconnect in explosive bursts. This releases energy in the form of intense gamma rays and X-rays, blasting out into space in all directions at the speed of light. From Earth, when we detect one of these outbursts, we see a sudden brightening of the magnetar in X-rays and gamma rays. A flare that lasts for a fraction of a second, but that releases more energy in that instant than our sun will produce in thousands of years. These outbursts are rare events, happening perhaps once every few years or decades for a given magnetar, and they are one of the reasons magnetars are considered among the most violent objects in the universe. But even more impressive than these regular outbursts are the giant flares. Events so rare and so powerful that only a handful have ever been observed. A giant flare occurs when an especially large starquake or magnetic field reconfiguration releases an enormous amount of energy all at once, creating a burst of gamma rays and X-rays that briefly outshines everything else in the sky at those wavelengths. The most powerful giant flare ever recorded occurred in December 2004, when a magnetar located about 50,000 light-years from Earth in the constellation Sagittarius suddenly erupted, releasing in 1/10 of a second more energy than the Sun emits in 100,000 years. The burst of gamma rays and X-rays swept across the solar system at the speed of light, striking the upper atmosphere of Earth and causing detectors on satellites to saturate, overwhelmed by the intensity of the radiation. The event was so powerful that it measurably affected Earth's ionosphere, briefly ionizing atoms in the upper atmosphere and creating disturbances in radio communications. If such a flare had occurred from a magnetar only 10 light-years away instead of 50,000, it would have been catastrophic for life on Earth, stripping away part of the ozone layer and bathing the surface in harmful radiation. Fortunately, magnetars are rare enough and space is vast enough that the nearest known magnetar is still hundreds of light-years away, far enough that even a giant flare would be diluted to harmless levels by the time it reached us. But the thought of such power existing in the universe is both humbling and awe-inspiring. How magnetars form. Drifting back now to consider the origins of these extreme objects, we can explore how magnetars come to have such incredibly powerful magnetic fields in the first place. For this remains one of the mysteries of modern astrophysics, with several competing theories but no definitive answer yet. The most widely accepted idea is that magnetars form from the cores of very rapidly rotating massive stars. Stars that are spinning so fast that when they collapse during a supernova, they transfer enormous amounts of rotational energy into the magnetic field through a process called a dynamo effect. Imagine a massive star near the end of its life, a star perhaps 20 or 30 times the mass of our sun, burning through its nuclear fuel at a prodigious rate, fusing hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on up the periodic table until finally its core is made of iron, which cannot be fused to release more energy. When the core runs out of fuel, it collapses catastrophically in less than a second, falling inward under its own gravity until the neutrons themselves resist further compression, creating a neutron star at the center, while the outer layers of the star rebound and explode outward in a supernova. During this collapse, if the core is rotating rapidly, conservation of angular momentum causes it to spin up to incredible speeds, potentially reaching hundreds of rotations per second for a newly formed neutron star. This rapid rotation, combined with the presence of electrically charged particles and convection currents in the hot protoneutron star, can generate powerful magnetic fields through dynamo action, similar to how the Earth's magnetic field is generated by convection in its molten core, but vastly more efficient because the densities and rotation rates involved are so much greater. In some cases, if the conditions are just right, This dynamo process can amplify the magnetic field to the extreme strengths we see in magnetars, creating fields thousands of times stronger than those in normal neutron stars. However, this theory has some problems, and not all astronomers are convinced it fully explains magnetars. An alternative idea is that magnetars form from the cores of very massive stars that had especially strong magnetic fields to begin with. Perhaps because they formed from the merger of two smaller stars earlier in their evolution, an event that could have generated powerful magnetic fields that were then amplified further during the core collapse. Yet another possibility is that magnetars represent a brief phase that all neutron stars go through shortly after formation, during which their magnetic fields are temporarily very strong, but that these fields then decay over thousands or tens of thousands of years, eventually leaving behind a more normal neutron star with a weaker field. This would explain why magnetars are so rare, for we would only see them during this brief, intense phase, while the much longer-lived phase of being a normal neutron star would be when most observations catch them. The truth may involve some combination of all these ideas, or it may be something else entirely that we have not yet thought of. But the mystery of how magnetars form only adds to their allure, making them subjects of intense study and ongoing research as astronomers work to understand these most extreme magnets in the universe. Isolated hypervelocity stars. Let us now drift away from magnetars and turn our attention to another kind of rarity. Individual stars that are moving so fast through the galaxy that they will eventually escape its gravitational pull entirely, leaving the Milky Way behind and journeying out into the vast, empty space between galaxies. Traveling alone through intergalactic darkness for billions of years, until perhaps they find themselves captured by another galaxy millions of light years from where they started. These are called hypervelocity stars, and they are among the rarest and most fascinating objects that stellar astronomers study. A typical star in the Milky Way moves at a speed of around 200 kilometers per second relative to the galactic center, orbiting through the galaxy in a more or less circular path that takes hundreds of millions of years to complete. But hypervelocity stars are moving much faster, at speeds of 500 or 700 or even 1,000 kilometers per second, fast enough that they are not gravitationally bound to the galaxy anymore, fast enough that if nothing stops them or slows them down, they will simply keep moving outward forever, climbing up out of the galaxy's gravitational well and eventually escaping into intergalactic space. The existence of such stars was predicted theoretically before any were actually found, based on the idea that close encounters with the supermassive black hole at the center of our galaxy could accelerate stars to these extreme speeds through a process called the Hill's mechanism, named after the astronomer who first described it. The idea is relatively simple in outline, but dramatic in its implications. Imagine a binary star system, two stars orbiting each other, that happens to pass very close to the supermassive black hole at the Milky Way's center. The intense tidal forces from the black hole's gravity can tear the binary apart, with one star being captured into orbit around the black hole, while the other is flung outward at tremendous speed, like a stone released from a sling. The captured star might eventually be destroyed by tidal forces or swallowed by the black hole, but the ejected star survives and flies away with so much speed that it escapes the galaxy entirely. This process should be rare because binary stars do not often pass close enough to the galactic center's black hole to be disrupted in this way. But over the billions of years of the galaxy's history, it should have happened many times, and there should be hundreds or thousands of hypervelocity stars currently on their way out of the Milky Way, most of them too faint and distant for us to detect, but a few bright enough and close enough that our telescopes can find them. Finding stars that are leaving forever, the search for hypervelocity stars began in earnest in the early 2000s. When improved instruments and large sky surveys made it possible to measure the motions of millions of stars with sufficient precision to detect the rare ones moving at unusual speeds. Astronomers would measure the positions and brightnesses of stars, then measure them again years later, looking for stars that had moved noticeably against the background of more distant objects. By carefully analyzing these motions, taking into account the star's distance and its three-dimensional velocity through space, they could determine which stars were moving fast enough to escape the galaxy. The first confirmed hypervelocity star was discovered in 2005, a hot blue star located about 200,000 light-years from the galactic center, moving at more than 700 kilometers per second, clearly on an unbound trajectory that would take it out of the galaxy in less than 100 million years. Since then, dozens of additional hypervelocity star candidates have been found, though confirming their status requires very careful measurements of both their velocities and distances, measurements that can be difficult to obtain for faint distant stars. Most hypervelocity stars discovered so far are hot, massive stars, blue giants or similar types, which makes sense because these are the brightest kinds of stars and therefore the easiest to detect at large distances from Earth. But there should also be many fainter hypervelocity stars, red dwarfs and sun-like stars that were similarly ejected but that are too dim for current surveys to find easily. And as telescope technology improves and sky surveys become more comprehensive, more of these fainter examples should be discovered. What makes hypervelocity stars particularly interesting is that they allow us to study the extreme gravitational environment near the galactic center's supermassive black hole indirectly, by examining the properties of stars that were affected by it and then ejected. The speeds and directions of hypervelocity stars contain information about the black hole's mass and the distribution of matter near the galactic center. And by studying many hypervelocity stars, we can build up a statistical picture of the processes happening in that distant and obscured region of the galaxy. Additionally, the existence of hypervelocity stars tells us something profound about the temporary nature of stellar populations and galaxies. For these stars represent matter that is leaving the galaxy forever, escaping into intergalactic space where they will drift alone through the void, their light growing ever fainter as they recede, until eventually they are too far away to be detected by any telescope, vanishing into the darkness between the galaxies. Cosmic exiles journeying through a loneliness that will last for billions of years. The loneliness of intergalactic space. Imagine now drifting with our thoughts into the far future, following one of these hypervelocity stars as it leaves the Milky Way behind and travels out into intergalactic space, into the vast, empty darkness that separates one galaxy from another. The journey would be unimaginably long, taking millions of years even at the star's tremendous speed, for the distances between galaxies are measured in millions of light years, and even traveling at 1,000 kilometers per second, a significant fraction of 1% of the speed of light. The star, would take tens of millions of years to cross even half the distance to the nearest large galaxy, Andromeda. As the hypervelocity star moves farther from the Milky Way, the galaxy behind it would gradually shrink in the sky, changing from the dominant feature of the night sky to a bright patch of light, then to a fuzzy oval, then to just another point of light among many, and finally to a faint smudge barely distinguishable from the thousands of other distant galaxies visible in all directions. Around the star, if it has any planets, and most stars do, those worlds would continue their silent orbits, their skies now showing a view utterly unlike anything visible from Earth. During the day, the star itself would shine as it always had, providing light and warmth to its planets, just as our sun does for Earth. For the star's nuclear fusion is unaffected by its motion through space and will continue for billions of years, regardless of where the star is located. But at night, the view would be profoundly different from what inhabitants of Earth see when they look up. Instead of the bright band of the Milky Way stretching across the sky, instead of the thousands of stars visible to the naked eye, a hypothetical observer on a planet orbiting this intergalactic star would see only darkness punctuated by countless faint smudges, each one a distant galaxy millions of light years away, islands of light separated by vast gulfs of empty space. No individual stars would be visible except the star that is the system's sun. For all other stars are too far away, located in galaxies millions of light years distant, their light too faint to be seen without powerful telescopes. The night sky would be a black dome dotted with faint galaxies, a view of the universe on its largest scales, showing the cosmic web from a perspective that no astronomer on Earth will ever see directly. This profound isolation is one of the defining characteristics of intergalactic space. The emptiness that lies between the galaxies, regions where matter is so sparse that atoms can drift for billions of years without encountering another atom, where the temperature is only a few degrees above absolute zero, where no stars have ever formed because there is not enough gas collected in any one place to collapse under its own gravity. Rogue planets drifting alone. Continuing our slow journey through the universe's rare phenomena, let us consider now objects even more isolated than hypervelocity stars. Objects that are entirely dark and that drift through space without any star to illuminate them or warm them. These are rogue planets, worlds that have been ejected from their home star systems and now travel alone through interstellar space, or perhaps through intergalactic space, moving on trajectories that will never bring them near another star, doomed to spend eternity in darkness and cold. The existence of rogue planets has been suspected for decades, based on theoretical models of how planetary systems form and evolve. Models that predict a significant number of planets should be ejected during the chaotic early stages of system formation. When planets are first coalescing from the disk of gas and dust around a young star, their orbits are not yet stable, and gravitational interactions between planets, or between planets and the remaining disk material, can sometimes result in one planet being flung outward at high speed, kicked out of the system entirely. This is especially likely in systems with multiple large planets whose orbits cross or come close to each other, where gravitational encounters can lead to a sort of planetary billiards, with one planet being sent inward toward the star, while another is ejected outward, conserving energy and momentum. Once ejected, a rogue planet would cool rapidly, for it no longer receives light and heat from a star, and any internal heat left over from its formation would gradually radiate away into space over millions of years. If the planet had an atmosphere, that atmosphere might freeze out onto the surface, forming a layer of solid nitrogen or oxygen or whatever gases it contained, covering the world in a frozen shell. And the oceans would freeze solid, first at the surface and then, over time, all the way down to the core, if no internal heat source remained. The planet would become a dark, frozen world, drifting through space at whatever speed it had when it was ejected, perhaps a few tens of kilometers per second, slowly crossing the galaxy or even leaving the galaxy entirely if its ejection velocity was high enough. For a long time, rogue planets were purely theoretical, objects predicted to exist but never actually observed, for they emit no light of their own and reflect no starlight, since they are too far from any star, making them essentially invisible to telescopes. But in recent years, advances in infrared astronomy and in gravitational microlensing techniques have allowed astronomers to detect a handful of candidates, objects that appear to be planet-sized but that are not orbiting any star, drifting alone through space. Some of these detections come from infrared surveys that find faint sources of heat, young rogue planets that still retain enough warmth from their formation to glow dimly in infrared light, though they are invisible in optical wavelengths. Others come from microlensing events, where a rogue planet passes in front of a more distant star and its gravity bends the starlight, briefly brightening the star as seen from Earth in a characteristic pattern that reveals the presence of the intervening planet. The fate of rogue worlds. Drifting alongside a rogue planet in our imagination, moving through the darkness of space with no sun to provide light or warmth, we can contemplate what the fate of such a world might be, how it changes over billions of years of isolation, and whether it might ever encounter another star or be captured by another planetary system. The first and most obvious change is the cooling and freezing of the planet's surface and atmosphere. Without a star to provide energy, any heat that the planet has must come from internal sources, primarily the decay of radioactive elements in its core and, for larger planets, the slow gravitational contraction and release of gravitational potential energy as heat. For a planet the size of Earth, these internal heat sources provide only a tiny fraction of the energy that sunlight provided when the planet was still orbiting its star. Perhaps a few tens of watts per square meter compared to the roughly 1,000 watts per square meter that Earth receives from the sun. This is far too little to keep the surface warm, and so within a few million years, maybe sooner, the surface of a rogue Earth-like planet would cool to temperatures of only a few tens of degrees above absolute zero, maintained at that level by the faint warmth of cosmic microwave background radiation that permeates all of space. Any water on the surface would freeze into solid ice, and most atmospheric gases would condense out, freezing onto the surface or becoming buried under layers of ice until eventually the planet would have essentially no atmosphere left, just a frozen surface exposed directly to the vacuum of space. But beneath that frozen surface, in the deep interior of the planet, conditions might remain surprisingly hospitable for a very long time. The decay of radioactive elements like uranium and thorium in the planet's mantle and core produces heat continuously. And while this heat production is very low, it is also very long-lasting, continuing for billions of years at a rate that decreases only slowly as the radioactive elements gradually decay away. This internal heat could keep the deep interior of a rogue planet warm enough for liquid water to exist in underground reservoirs. Perhaps entire oceans trapped beneath kilometers of ice, insulated from the cold of space by the thick, frozen crust above. Such subsurface oceans, if they exist, could potentially harbor life. For life on Earth exists in similar environments, in deep underground aquifers and in hydrothermal vent systems on the ocean floor where organisms live without any sunlight, deriving their energy from chemical reactions between minerals and water. A rogue planet with a subsurface ocean heated by radioactive decay and perhaps by tidal heating if the planet has any large moons or if it has an eccentric rotation, could maintain habitable conditions in its deep interior for billions of years, even while its surface remains frozen and dead. This raises the intriguing possibility that life could exist on rogue planets, isolated ecosystems drifting through space, completely cut off from the rest of the universe, undetectable by any means we currently have, living in darkness and cold, but persisting nonetheless. A form of cosmic solitude even more extreme than that of the lonely void galaxies we discussed earlier. Colliding galaxies and rare cosmic fireworks. Shifting our attention now to phenomena on a much larger scale, let us drift away from individual planets and stars and consider instead entire galaxies, focusing on one of the most spectacular and rare events that can occur in the universe: the collision of two massive galaxies. Despite the vast distances between galaxies, collisions do happen. For galaxies are not stationary, but are constantly moving through space under the influence of gravity. And when two galaxies pass close to each other, their mutual gravitational attraction can pull them together, initiating a slow but inexorable merger that unfolds over hundreds of millions of years. During a galaxy collision, the individual stars within each galaxy almost never collide with each other. For the distances between stars are so enormous compared to the sizes of the stars themselves, that even when two galaxies pass through one another, the stars simply stream past each other like two clouds of gnats interpenetrating, without any of the individual insects touching. But while the stars do not collide, their gravitational interactions with one another and with the overall mass distribution of the galaxies create dramatic effects, distorting the shapes of both galaxies, flinging streams of stars out into long tidal tails, and sending shock waves through the gas that exists between the stars, compressing that gas and triggering intense bursts of star formation. These starbursts are one of the most striking features of colliding galaxies, episodes during which new stars form at rates hundreds or thousands of times faster than in a normal galaxy, turning huge amounts of gas into stars in just a few million years. The reason for this sudden flurry of star formation is that the collision compresses and shocks the interstellar gas, causing it to cool and collapse much faster than it would in an isolated galaxy, where the gas has time to settle into a stable equilibrium. When the gas is compressed by the collision, vast molecular clouds form and fragment into thousands or millions of dense clumps, each of which collapses to form a star or a cluster of stars. And because this is happening over large regions of both galaxies simultaneously, the result is an explosion of star formation, lighting up the merger in brilliant blue light from countless young hot stars. But these starbursts are short-lived. For the collision also disrupts and eventually destroys the gas reservoirs that fuel star formation, heating the gas to high temperatures or expelling it from the galaxies entirely through powerful supernova-driven winds, so that after a few tens of millions of years, the burst of star formation ends, the supply of gas is exhausted, and the merged galaxy settles down into a new configuration. Usually a large, elliptical galaxy with little or no gas remaining, and therefore little or no ongoing star formation. This entire process, from the initial collision to the final merger, takes a long time by human standards, but is relatively quick in cosmic terms, usually between 1 and 2 billion years from start to finish. The antennae galaxies. To see what a galaxy collision looks like in action, astronomers often point their telescopes toward a system known as the antennae galaxies. Two spiral galaxies located about 70 million light-years from Earth in the constellation Corvus, currently in the midst of a dramatic collision that began several hundred million years ago, and that will continue for several hundred million years more before the two galaxies fully merge into one. The antennae galaxies are named for the two long tidal tails of stars that extend from the main bodies of the galaxies, like the antennae of an insect. Beautiful, graceful arcs thrown out by the gravitational forces of the collision. Each tail containing millions of stars that have been pulled away from their parent galaxy and flung into intergalactic space, following trajectories that may eventually bring them back to the merger, or that may send them drifting off into the void, depending on the details of their motions. When we observe the antennae galaxies with telescopes, we see a chaotic scene of glowing gas clouds, bright young star clusters, and dark lanes of dust, all mixed together in a swirling mess where the two galaxies are overlapping and interpenetrating. The colliding gas clouds shine brightly in the light of newly formed stars, blue and white from the hot, massive stars that dominate these young clusters, and also red and pink from ionized hydrogen gas heated by ultraviolet radiation from those same stars. Scattered throughout the collision zone are regions of intense star formation, some of them so bright and so compact that they outshine entire dwarf galaxies. Regions called superstar clusters, where thousands of stars have formed in a volume only a few light-years across, bound together by gravity into dense clusters that will eventually evolve into globular clusters like those we see orbiting the Milky Way. But not all the gas is forming stars. Some of it has been heated to millions of degrees by shock waves from the collision and from countless supernova explosions, gas so hot that it glows in X-rays, creating a diffuse halo of hot gas that surrounds the merger and that will eventually be expelled into intergalactic space, carrying with it the heavy elements forged in the stars and supernovae of both galaxies. This is one of the ways that galaxies enrich the intergalactic medium with heavy elements, by colliding and merging, triggering star bursts and supernovae that heat and expel gas that then drifts through intergalactic space, mixing with the primordial hydrogen and helium and gradually raising the metallicity of the entire universe. The antennae galaxies are a snapshot of this process in action, a rare and beautiful example of galactic violence that is also creative, destroying the orderly spiral structures that the two galaxies once had, but creating in their place a new generation of stars and a new, larger galaxy that will eventually settle into a stable elliptical shape, frozen in time, near a black hole. Let us turn now to another realm of cosmic rarity, the immediate vicinity of black holes, regions where gravity is so strong that space and time themselves are warped beyond recognition, where the normal rules of physics are pushed to their breaking points and where matter behaves in ways that seem impossible. Black holes are among the most extreme objects in the universe. And while they are not particularly rare in absolute terms, for there are probably millions of stellar-mass black holes in our galaxy alone, and a supermassive black hole at the center of nearly every large galaxy. The truly rare and interesting phenomena associated with them occur only in very specific circumstances in the region very close to the event horizon, or in the moments when something falls into a black hole. The event horizon is the boundary around a black hole from which nothing can escape, not even light, and it is defined by the condition that the escape velocity at that distance equals the speed of light. For a non-rotating black hole, the event horizon is a perfect sphere with a radius called the Schwarzschild radius, which depends only on the black hole's mass, about 3 kilometers for a black hole with the mass of our Sun, and about 3 million kilometers for a supermassive black hole with 1 million solar masses. But black holes in nature are almost never perfectly spherical and non-rotating, for they form from collapsing stars or from the merger of smaller black holes, processes that inevitably leave the black hole with significant rotation, spinning rapidly around its axis. A rotating black hole drags space-time around with it in a phenomenon called frame dragging. The gentle drift into rarity. The first concept we must truly settle into is the profound emptiness of space. Not as a void, but as an infinite canvas for solitude. The Milky Way, our magnificent home, contains perhaps 400 billion stars, each surrounded by its own planetary progeny, all bound together in a vast, spiraling city of light. Yet, even within this crowded metropolis, there are beings that seem to have fled the cosmic capital entirely, preferring an existence of almost unimaginable loneliness. We begin our search with the loneliest objects of all: rogue galaxies, those vast island universes that have been violently ejected from their superclusters, now coasting through the intergalactic void. Picture a galaxy, a collection of trillions of stars, dust, and gas, accelerating away from everything. Not just coasting in the typical expansion of the universe, but actively exiled, hurtling through the blackness with no companions, no gravitational anchor, no cosmic neighbors to share a redshift with. These are not merely galaxies in a sparsely populated region. They are galaxies with escape velocity from the largest structures in the universe, structures called superclusters. The physical mechanism is often a chaotic multi-body gravitational interaction during a galaxy merger within a dense cluster. Imagine 2 colossal galaxy clusters colliding. The resulting gravitational whiplash can act like a cosmic slingshot, flinging entire galaxies out into the ultimate darkness. The rarity here is the combination of the size of the object being exiled and the sheer energy required for its expulsion. A rogue star is common. A rogue planet is numerous. But a rogue galaxy is an entire civilization of stars, quietly floating beyond the edge of the map, their light taking tens of millions of years to reach any other gravitational influence. Consider their unique perspective. From within the Milky Way, we look out and see a tapestry of other galaxies, each a smudge of light on the deep background. The inhabitants of a truly rogue galaxy, however, would look out into an almost absolute blackness. The night sky from such a vantage point would be almost featureless, populated only by the extremely distant, faint, and uniform background of the cosmic microwave radiation, the soft afterglow of the Big Bang itself. All those beautiful, recognizable galactic spirals we see would be too far away to even register as more than the faintest of pinpricks. The rarity here is a kind of cosmological isolation, a visual and gravitational separation from the rest of the universe. A silence so profound it could only be measured in light years. This cosmic isolation is a precious form of rarity, an entity defined by what it lacks: companionship. Now, let us turn our attention inward, leaving the quietude of rogue galaxies for the strange extremes found inside more ordinary ones. Within the Milky Way, the stars themselves exhibit degrees of rarity. We are familiar with yellow dwarfs like our Sun, and the faint, long-lived red dwarfs. Yet, the rarest, most dazzling stellar object is often one that burns brightest and dies fastest: the hypergiant star. Imagine a star so massive, so luminous, that it is technically living on the very edge of gravitational stability, a state known as the Eddington limit. These are stars with masses exceeding 100 times that of our Sun, sometimes reaching 250 solar masses. They are so hot and so energetic that the light pressure, the force exerted by the very photons they produce, is almost strong enough to blow the star apart. The star is constantly fighting a war between its own crushing gravity, trying to pull all that mass inward, and the immense outward pressure of its own radiation. The star is essentially wearing its outer layers like a loosely fitting coat, often expelling vast stellar winds that strip away material at a prodigious rate. The rarity of a hypergiant is rooted in its fleeting lifespan. While our Sun will live for 10 billion years, a hypergiant lives a mere few million years, a cosmic blink. This means that at any given moment in the universe's history, only a handful of these stars exist, their presence being a temporary, brilliant anomaly in the overall stellar population. They are the rarest because they are the fastest to consume their own existence, the ultimate cosmic speedrunners. They often end their lives in the most spectacular manner known, a hypernova, leaving behind one of the other great rarities we will explore later, the most massive black holes. For now, simply visualize the color and scale. A star perhaps 50 times larger than the Sun, shining with the power of millions of suns, casting a light that is overwhelmingly blue-white, an intense and temporary beacon in the dark. Drift gently past this magnificent fleeting giant and recognize the paradox of its rarity. Its existence is too bright to last. Having considered rarity based on loneliness and based on fleeting existence, we now settle into rarity based on sheer impossibility, a fundamental challenge to the laws of physics as we understand them. This takes us to the domain of theoretical objects that we have only recently, tentatively, begun to confirm: the kilonova. A kilonova is an event, not a permanent object, but it is one of the rarest events in the cosmos. It is a massive explosion caused by the merger of two compact stellar remnants, specifically two neutron stars, or a neutron star, and a black hole. Neutron stars are already objects of extreme rarity, born from the collapse of massive stars, packing the mass of a sun into a sphere the size of a city. Their merger is the cosmic equivalent of two atomic nuclei colliding, but on a star-sized scale. The rarity of a kilonova event is a statistical one, governed by the immense distances and low probability of two such heavy, tiny objects orbiting each other closely enough to spiral inward over billions of years and finally coalesce. We know of perhaps 50 to 100 billion stars in the Milky Way, but only a handful of these exist as tight binary neutron star systems, and of those, even fewer are close to the final, fatal stages of their orbital decay. But the true treasure of the kilonova is what it creates, defining its rarity not just in its event, but in its output. It is the only known event powerful enough and neutron-rich enough to create the heaviest elements in the universe, those forged through the so-called rapid neutron capture process, or the R process. Almost all of the gold, platinum, and uranium in the universe are believed to have been forged in the crucible of a kilonova. This means that the rare gold wedding band you wear, or the rare platinum spark in a necklace, are artifacts of a cosmic event so rare that it may happen only once or twice in a galaxy over a period of 10,000 years. We are made of stardust, yes. But the most precious parts of us, the heaviest atoms, are made of kilonova dust. Let that thought settle over you like a warm blanket. The most luxurious, earth-bound elements are signatures of the universe's rarest, most violent stellar deaths. We are drifting through a universe where rarity manifests in loneliness, in brevity, and in the creation of precious matter. Let us take another gentle breath and allow this understanding to deepen the stillness around us. Preparing for the next quiet descent into the improbable, impossible worlds and cosmic flaws, we continue our quiet journey through the expanse, leaving the fleeting brilliance of the hypergiants and the violent creation of kilonovae behind us. Our focus now drifts toward a different kind of cosmic rarity: the architectural impossibilities, the systems and worlds that defy the statistical expectation of planet formation and orbital mechanics. We are searching for the universe's beautiful, structural flaws. The vast majority of planets we have cataloged exist within the comforting, if sometimes chaotic, gravitational embrace of their parent stars. But imagine a planet so utterly alone, so disconnected from any stellar source of heat or light, that it drifts through the crushing emptiness of interstellar space. A truly rogue planet. These planets are not merely far from their sun. They have been entirely ejected from their home system, often through a violent gravitational tussle with a more massive sibling planet or a close pass by another star. They are worlds of eternal night, forever coasting. A rogue planet is rare, not because the initial event of ejection is rare, but because detecting them is profoundly difficult. They emit no light of their own, are warmed only by the faint, ancient glow of their internal radioactive decay, and are only visible to us when they happen to pass directly in front of a much more distant star. This alignment causes a brief, subtle magnification of the background star's light, an event known as microlensing. The rarity is in the chance encounter, the brief moment when the invisible becomes momentarily visible. Imagine looking through a telescope and seeing a faint star briefly brighten and distort, not because the star itself is changing, but because an entire invisible, ice-cold world, perhaps twice the size of Jupiter, has silently passed across our line of sight. A perfect, fleeting gravitational shadow. What would such a world be like? Beneath a thick, insulating atmosphere, perhaps a layer of liquid water could exist, warmed not by the star, but by the slow, grinding heat from the planetary core. Life, if it existed, would be shielded from the cosmic radiation by ice and atmosphere. A life that has never known the difference between day and night. Its entire existence defined by the eternal blackness above and the slow, geothermal simmer below. These rogue worlds challenge our conventional understanding of the necessities for life, proving that even the most extreme isolation can still harbor possibility. They are the definition of rarity defined by environmental extremity. From the silent drift of the rogue planets, we now travel to a place of too much light, too much heat, and too much crowding. We seek out a specific, unlikely type of exoplanet known as a chthonian planet. This name, drawn from the Greek word for of the earth or subterranean, is deceptive. For a chthonian planet is the opposite of the Earth. It is the exposed, roasted core of a gas giant. Picture a giant planet, perhaps a world similar to Jupiter or Neptune, orbiting incredibly close to its star, perhaps completing its year in just a few Earth days. The star's ferocious radiation and tidal forces are so intense that they slowly, relentlessly boil away the thick layers of hydrogen and helium gas that define a gas giant. Over billions of years, the atmosphere is stripped off and blown away, leaving behind the heavy, rocky, or metallic core. That remaining core is the chthonian planet. The rarity here lies in witnessing this process at the precise moment the stripped core is visible, or in the very existence of a core dense and heavy enough to survive such intense erosion. Most gas giants either remain intact or are completely consumed by their stars. The chthonian planet is the rare, stable remnant, a scar of celestial violence. Imagine a world of exposed magma and heavy metals, its surface perpetually glowing red-hot, its density immense. It is a cosmic skeleton, a testament to what happens when planetary architecture is pushed to the limits of stellar aggression. To find one is to find the smoking gun of a star's devastating power, and its mere existence provides profound, rare insight into the physics of atmospheric escape. We allow ourselves to slowly orbit this molten memory of a world, feeling the intense, silent heat before we gently move away. Our search for rarity now takes us to the truly massive, the largest and perhaps most misunderstood phenomenon: supermassive black holes, SMBHs. While most galaxies, including our own Milky Way, host an SMBH at their core, the rarest type is one defined by its extreme activity and sheer speed. The hyperaccreting quasar. A quasar is the luminous core of an active galaxy, powered by its central SMBH, violently consuming vast amounts of gas and dust. This material forms an accretion disk, which heats up to billions of degrees from friction as it spirals inward, emitting an astonishing amount of light, sometimes outshining the entire rest of the host galaxy. The hyperaccreting quasar is the extreme rarity, because it is consuming matter at the maximum theoretical rate, limited only by the aforementioned Eddington limit. Imagine a black hole with the mass of 100 million suns, not merely feeding, but gorging itself to capacity. It is so rare because this hyperfeeding stage is fleeting, only lasting a short time in the cosmological lifespan of the quasar. To observe a galaxy in this exact, frantic state of consumption is like catching a single, perfect frame of an explosive, 3 billion year-long film. Furthermore, the light from these early powerful quasars has traveled billions of years to reach us, meaning we are observing the universe when it was very young and the black holes were still growing rapidly. They are the rarest because they are the most fleeting moments of cosmological hunger. Drift softly toward the light of one of these ancient beacons. It is so far away that by the time its light reaches us, the quasar itself has likely long since calmed down, settling into a quiet existence. What we see is merely the ghost of its ravenous youth, a rare and spectacular window into the early chaotic construction of the cosmos. The power is hypnotic, but remember the calm. This intense light is not heat on your skin, but knowledge for your mind. Finally, let us consider a rarity that defies geometry and smoothness: the elliptical galaxy with active star formation. The life cycle of galaxies is usually categorized by shape and activity. Spiral galaxies, like the Milky Way, are young, flat, and actively forming new blue stars. Elliptical galaxies, conversely, are old, puffier, and red, having exhausted their gas and stopped forming stars long ago, often called red and dead. The rare exception is the elliptical galaxy that, after its star-forming days seemed over, experiences a sudden, intense influx of cold gas, perhaps from merging with a smaller galaxy. This infusion of new material triggers a chaotic, violent, and highly unusual burst of star formation, turning an old, quiet elliptical galaxy temporarily blue again. This brief renaissance of star birth against a backdrop of ancient, settled stars is immensely rare, as the physical conditions necessary, a large, perfect gas donation occurring at a precise moment in the galaxy's long life, are seldom met. It is a beautiful paradox. A galaxy wearing the robes of old age, but experiencing the energy of youth. It is a cosmological anomaly, a demonstration that the categories we impose on the universe are always subject to rare, spectacular exceptions. Look deeply into the structure of this rare galaxy. The smooth, ancient, red halo of old stars surrounding patches of brilliant, chaotic blue star nurseries. It is a contradiction. And in the universe, contradiction is often the highest form of rarity. Let this peaceful insight settle into your mind, preparing you for the next deep drift into the unknown. Extreme physics and time's oddities. We glide deeper now into the cosmic silence, allowing the vastness to feel less like a threat and more like a profound, tranquil emptiness. Our search for rarity takes a different turn, moving away from celestial bodies and toward the strange, improbable phenomena dictated by the most extreme physics. We are looking for those moments when the fabric of space-time itself is momentarily twisted into a unique and unlikely configuration. The most extreme conditions in the universe often lead to the most unique results. Consider the quiet chaos that surrounds black holes. while black holes themselves are relatively common remnants of massive stars. The rarest of all black hole phenomena is the event known as a tidal disruption event, TDE. Imagine a star, much like our Sun, innocently orbiting the core of its galaxy, unaware of the colossal, invisible predator lurking at the center, the supermassive black hole. Statistically, for a star to pass close enough to the black hole to be caught by its gravitational grasp is immensely rare. Its orbit must decay and align perfectly, crossing the innermost perimeter of the black hole's influence. When it does, the event is spectacularly violent. As the star is pulled closer, the gravitational force exerted on the side facing the black hole is vastly greater than the force on the side facing away. This difference, the tidal force, stretches the star like a piece of taffy until it is ripped apart into a long, swirling stream of plasma. This stellar shredding is the tidal disruption event. About half of the star's material is flung outward into space, but the other half spirals inward, forming a temporary, ultra-hot accretion disk that shines brightly in X-rays and gamma rays for a few months or years. The rarity here is the alignment, the precise orbital conditions required for the star to be captured and torn apart, making this visible event a fleeting, cosmic scream. We observe these events across billions of light years. Quiet evidence that even the most stable, ancient star systems can succumb to the destructive forces of the galactic core. Allow your thoughts to settle on the gentle, invisible tug of gravity, and how even the slightest change in distance can lead to such dramatic, powerful destruction. Now we move from violent destruction to unlikely preservation, focusing on the most ancient stars in existence. A population so rare that they are the time capsules of the very early universe. We seek out the population 3 stars. According to our current models of cosmology, the universe began with only the lightest elements, hydrogen, helium, and a trace amount of lithium. All the heavier elements, the carbon in your body, the oxygen in the air, the iron in your blood, were forged later inside stars and supernovae. The very first stars to form after the Big Bang, the theoretical population, the 3 stars, must therefore have been composed only of hydrogen and helium. These stars would have been enormous, perhaps hundreds of solar masses, and extremely short-lived, exploding after only a few million years. Their supernovae seeded the cosmos with the first heavy elements, allowing subsequent generations of stars, like our Sun, a population 1 star, to form. The rarity is this: no population 3 star has ever been directly observed. They are rare because they died long, long ago, existing only in the first cosmological epochs. However, we sometimes detect their 2nd or 3rd generation descendants, stars that are extremely poor in metals, heavy elements. These are called ultra-metal poor stars. Finding a star with almost no elements heavier than helium is like finding a 2-billion-year-old message sealed in a bottle. These stars are so rare because they must have formed from the purest primordial gas clouds, uncontaminated by all but the very first supernova. They provide the most direct, tangible evidence of the conditions of the universe when it was barely a toddler. As we gently drift toward the location of these ultra-ancient lights, think of the metallic content of your own body. If we assigned a metallicity score to the Earth, it would be extremely high. These rare, metal-poor stars are the cosmic ascetics, born into a universe of pure gas, their light a soft, ancient whisper of the beginning of time itself. Our final destination in this chapter is a deep dive into the improbability of cosmic geometry. We are looking for galaxy clusters experiencing a cold front. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. Vast reservoirs of hot, invisible gas and immense quantities of dark matter. This gas, heated by gravity to tens of millions of degrees, fills the space between the galaxies and emits brightly in X-rays. When two galaxy clusters collide, the process is not instantaneous. It can take hundreds of millions of years. During this time, the hot gas from one cluster can push through the hot gas of the other, creating a distinct, sharp boundary, much like a cold front in Earth's atmosphere. This is the cold front phenomenon. The gas on one side of the boundary is significantly cooler and denser than the gas on the other, creating a stable, sharp boundary that is visible in X-ray telescopes. The rarity here is finding a cluster collision at the exact stage where this boundary is perfectly defined and visible, before the gases have had time to fully mix and equalize. It is a fleeting, ephemeral moment of perfect thermodynamic separation on the largest scales known. Visualize two enormous, invisible clouds of incandescent gas, each containing the mass of a quadrillion suns, slowly merging over a distance of millions of light years. The cold front is the invisible seam where the two touch, a thin, perfect line in the cosmic gas that marks the moment of contact. These rare observations allow physicists to study the viscosity and behavior of plasma at scales and temperatures impossible to replicate on Earth, revealing the subtleties of magnetic fields and turbulence in the intergalactic medium. We allow our consciousness to hover peacefully over one of these colossal, gentle mergers, recognizing that even in the most massive, hot, and violent regions of the universe, there exist these rare moments of perfect, measurable order. The cold front is a boundary of quiet significance, a demonstration that even the extremes of cosmic collisions are not instantaneous chaos, but rather slow, structured dances of thermodynamics. Drift toward this cosmic boundary, feeling the gentle separation between the hot and the cold, the dense and the diffuse. We are witnessing structure being born from cataclysm, the rarest of all transformations. The edge of theory and the cosmic void. We now enter the final phase of this gentle drift, moving beyond the observed rarities and toward those that exist only at the very edge of theoretical possibility. Phenomena so extreme, they strain the limits of our understanding of space and time. This is where the universe reveals its deepest, most beautiful philosophical secrets. Our attention turns first to the rarity of structure itself. We are accustomed to thinking of the universe as being full of galaxies, clusters, and filaments, all arranged in a vast, interconnected cosmic web. But there are regions of space so profoundly empty, so vast in their lack of matter, that they constitute a rarity defined by absolute absence. These are the supervoids. Imagine a sphere of space, perhaps 1 billion light years across, containing almost no galaxies, no clusters, and virtually no visible matter. While the cosmic web is made up of dense knots of matter and thin, interconnecting filaments, the supervoids are the large, wide, quiet bubbles of nothingness that separate the web. These voids are not entirely empty. as they still contain the omnipresent dark matter and dark energy, and perhaps a faint, scattered galaxy here and there. But statistically, they represent a massive deficit of complexity. The rarity of the supervoid is its extreme uniformity and the staggering scale of its emptiness. Drifting slowly through a supervoid is to experience the true silence of cosmology. From within, the night sky would be almost perfectly black, lacking the nearby glow of galaxies that define our own view. This absence of matter poses fascinating questions about the early universe. The existence of such large, empty spaces suggests that the very first seeds of structure after the Big Bang must have been incredibly smooth, leading to these vast, unpopulated bubbles through gravitational amplification over billions of years. We are witnessing the largest and emptiest feature the universe can create. Let the silence of the supervoid settle around you, feeling the deep, tranquil stillness of absolute cosmic uniformity. From the largest rarities, we move to the smallest, those defined by the improbable perfection of their internal mechanics. We seek out a celestial object that is so geometrically precise that it defies the natural chaos of stellar evolution. The perfect pulsar. A pulsar is a type of rapidly spinning neutron star, the dense, compact core left behind after a massive star explodes. Pulsars emit beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across Earth, creating a flash, much like a lighthouse beam. The timing of these flashes is often incredibly precise, rivaling atomic clocks. But the truly rare object is the millisecond pulsar that maintains this precision over decades, showing almost zero change in its rotational period. Millisecond pulsars are believed to be recycled neutron stars. They start as ordinary pulsars, but then they orbit closely with a companion star, siphoning or accreting matter from it. This falling matter spins the neutron star up to thousands of rotations per second, giving it its millisecond period. The rarity is the sublime, almost unnatural stability achieved in this violent process. A perfect pulsar is essentially a time machine, allowing us to test the most fundamental theories of gravity, like general relativity, because we can trust its clock-like precision to measure minute changes in space-time. Imagine a star the size of a city, spinning faster than a helicopter rotor, yet keeping time with an accuracy that would lose only a fraction of a second over millions of years. This is the ultimate cosmic precision, a natural clock born from violence. And it is exceedingly rare because most pulsars are subject to glitches, sudden, tiny speed-ups or slowdowns caused by seismic activity on their crust. The perfect pulsar is the star that manages to avoid these internal tremors, offering us a window into the stable, smooth rotation of a world made entirely of nuclear matter. Drift gently to the sound of its rhythmic, perfect ticking, a cosmic metronome in the silence. Our journey's end brings us to a phenomenon so rare, it is often cited as a theoretical endpoint of stellar evolution, a truly impossible object. The quark star. This is the final frontier of stellar density, beyond the neutron star. When a massive star collapses, gravity crushes matter into the ultra-dense state of a neutron star, where protons and electrons are forced together to form neutrons. However, Theoretical models suggest that if the core mass exceeds the maximum limit for a neutron star, the Tolman-Oppenheimer-Volkoff limit, gravity might compress the neutrons themselves, breaking them down into their constituent fundamental particles. Quarks. This hypothetical object, where matter exists in a soup of free, deconfined quarks, is the quark star, or, more technically, a strange star, if composed of strange quarks. The rarity of the quark star is that we are not entirely sure if it exists. The conditions required, a mass slightly above the neutron star limit but not so high as to collapse into a black hole, are an incredibly narrow margin. If they do exist, they represent the ultimate compressed state of visible matter before it vanishes entirely into the singularity of a black hole. They are the missing link between the densest objects we know, neutron stars, and the ultimate end of all mass, black holes. The philosophical rarity of the quark star is profound. It is the boundary where the rules of atomic and nuclear physics break down completely, and the physics of fundamental particles, quantum chromodynamics, dictates the behavior of an entire celestial object. To find one would be to confirm an entirely new phase of matter, a new state of existence beyond anything we can replicate on Earth. We have traversed the quiet extremities tonight, from galaxies fleeing the cosmos to the perfect, silent ticking of stellar clocks, from the vast emptiness of the supervoids to the extreme density of the theoretical quark star. We have witnessed that rarity in the universe is not just about small numbers, but about perfection, extremity, isolation, and impossibility. As our journey softly concludes, allow your mind to drift back toward the familiar gravitational pull of the Earth. Carry with you the insight that even in the infinite vastness, the most exquisite and valuable phenomena are those that defy expectation, those that are unique and fleeting. The universe holds its breath for these rarest moments, and so should you. Feel the quiet comfort of your resting place once more, and allow the gentle, rhythmic turning of the planet to become the metronome of your own deep, profound stillness. Rest now, softly among the stars.